All right, if there are no more questions, then we'll get started. Thankfully, there aren't a lot of material to cover today because graph neural networks are relatively simple. So hopefully we can make it in 1 hour. All right, graph neural networks. Yeah, we'll first talk about graph data a little bit and then move on to graph convolution, which is the essence of graph nets, and how it is related to graph, how graph convolution is related to conv nets or convolution itself, and then move on to the final chapter, which is graph neural networks and transformer, because the two are really closely related. So we're going to talk about the relationship between self-attention and graph convolution. All right, graphs. So graphs are data that consists of nodes and edges. So nodes being vertices and the edges being relations. So there are like A, G, C. These are all nodes. So there are a lot of nodes here, and the line between them are the edges. So I hope everybody at least knows this is a graph. So I guess if you studied computer science in undergrad, then you probably already are familiar with what data and with what graphs are, what graph is, because you've probably taken the algorithm classes. If you're not from computer science background, then maybe this is a time you can get familiarized with graphs. The theory behind graphs are really complex. There's like a whole lot of history behind graph itself, but today what we're going to talk about is going to be very surface level, so no worries there. So that so as I said, graphs consists of nodes and edges, and nodes could have some node specific features. For example, like A could be a person, and a person could have like different features like age or gender or like occupation, something like that. But it could or it could not. I mean, either way, there could be or there could not be node specific features. So if there are no node specific features, then each node is just a node. There are no features. And similar with edges. So edges could be, oh, this is important. So edges could be undirected or directed. So if there's an arrow like this, then this is a directed graph. But here, there is no, in this figure, there are no directions. So this is not a directed graph. This is an undirected graph. So all we know is that like some nodes are connected to each other, but there are no directions. And also there could be multiple relation types. So for example, if this was a social network and HNF4, like this is like a friends, but this could be like I don't know, maybe family. Like if this were like a graphs of people, then like each individual nodes could be people, and the edges could be different types of relationship between people, like friends, family, or married, something like that. All right, moving on then. So there are a lot of data sets that are actually graphs. So we can easily download these graph data sets from the internet. So Facebook friends are graphs. Web documents with links, so hyperlinks, they are also graphs because some documents are linked to each other. And road networks are also graphs. Chemical compounds, also graphs. They can be represented as graphs, and knowledge bases are also graphs. So let's look at some of them one by one. So friends network, in this case, so I just took a picture from the internet. So these like A, B, C, D, like these are all like people, and this is just friends network there. So there are only this is undirected. First of all, the nodes are unspecific, so we don't know anything specific about each people. Each node has no specific features. It's just a person. It's just a unique person, like distinct people. And the graphs are undirected. So because friends relationship does not have direction. If I'm friends with you, then you are friends with me. So there's no direction here. So and that's it. So it's just that. But friends social network or friends network itself is a super interesting data set, and it was actually a very hot topic since the beginning of SNS, social network service. So since Facebook came out and like Twitter came out, and like people were following each other, like, or Instagram also. So people were following each other, or people were friends with each other, and with that gigantic graphs, because why the reason I'm saying that it's gigantic is because Facebook accounts, I think there are at least like 2 billion face accounts or something, or 1 billion, 2 billion. So it's a graph with 1 or 2 billion nodes, and the edges are also like at least like several billions of edges. So what you can do is you can find influencers. So this is more like data mining rather than machine learning. So finding, like, studying or analyzing the friends network or social network and finding influencers so you can target them for advertisement. So you know, like, it was sort of an issue in Korea with a YouTube advertisement or commercial, like 뒷광고. So the corporations, when they want to advertise their products, they want to be as efficient as possible, pay the least amount of people, and maximize the advertisement effect. So they would find the influencers who are mostly connected to other people, or who are mostly viewed by other people. And also this could Facebook is really good at this, recommending friends. So you can find friends that you didn't even know existed. So that's all SNS analysis, social network analysis. Web documents, this is also a very old concept. So this is how PageRank made Google search possible. So PageRank is an algorithm for determining how important each documents are in the web. So in the web, there are trillions of web documents. So not just like billions, but trillions, or maybe even more. We really don't know how many documents there are on the web. And when I say documents, I'm talking about HTML documents. So HTML documents are linked to each other. So in PageRank, how Larry Page, the founder of Google, viewed web documents is the unspecific nodes. So when he came up with the algorithm PageRank, he didn't care about the contents of the node. So like the title of the page, or the contents, or text, or the images in the page, he didn't care about that. All he cared is that there are nodes, that there is a page in the web. So each web page is just a node, and the edges are directed. So the outgoing links are edges. So if there's a hyperlink that you can click and it leads to this page, then that's a directed relationship. And same with some document leading to this document, some other document leading to this document. So you can see that here the web page B has most incoming links from other web pages. So it has the largest circle, and also the score itself, the PageRank score itself is highest compared to others. So that's PageRank is basically the score of the importance score of each document in the web. So when you like do a search, or when you do a query, you can rank them in the first place when you're returning the search results. So this PageRank is calculated based on random walk. Like you start from somewhere, you start from this one, and then you randomly visit other websites, and the probability is determined by the links, the outgoing links. So for example, here E has outgoing links to F, D, and B, and you just take 33% chance of moving from one place to another, and then another random chance from moving place to another chance moving from, and then another random walk. Like you do a random walk like some number of times, and if you do that, then you'll converge on a score. Like a web document with a lot of incoming links will be visited a lot of times, which means that the more incoming links, the more valuable a web page is. So basically, that's how you calculate the PageRank. So web documents are graph data. Chemical structure. I also talked about chemical compounds. So chemical structure are also graph data. So again, the nodes are unspecific duplicate nodes. So I'm saying duplicate nodes because like the same atom, the element, it can be used multiple times. Like same carbon could be used multiple times. Like this is some chemical structure. And you can see that C, 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 C are used like 5 times. So it's no longer the fact that the nodes are unique. And again, and of course, the edges are now multi-type edges. It's still undirected because this is just like a connection. So it's just connected or not connected. So it's undirected, but there are single bond and double bonds. So this is a single bond, this is a double bond. So now you want to specify how 2 nodes or how 2 atoms are connected to each other. And this chemical compound or chemical structure are a hot topic these days because of all the AI and graph neural networks and BERT and all that. So drug development is a really super hot topic these days. Like people were trying to guess the best compound or best ingredient for COVID-19. I mean, best ingredient for drugs that could cure COVID-19, or they could be like the vaccine for COVID-19. So AI-driven drug discovery or AI-driven drug development is like where all the monies are these days. Also, another interesting thing is toxicity prediction. Like when you want to develop a drug, for example, or when you want to develop anything like human digestible, then you want to guess or predict is toxicity. Like some chemical compounds are toxic. So you want to predict the toxicity level of a compound. So in that case, you want to take a look at this chemical structure and then use graph neural networks and then obtain a graph representation and then plug it into like binary classifier, whether it's toxic or not. The last example is knowledge base. So knowledge base or knowledge graphs. Knowledge graph is a term used by Google, but knowledge base, knowledge graph, both are the same thing. So it's a graph representation of facts, like world knowledge, or it could be domain specific knowledge as well, like some medical knowledge or history knowledge or something like that. So in this case, it's just this example here is just a general common sense knowledge. And here you can see like Mona Lisa was painted by Da Vinci, or Louvre is located in Paris, and Paris is a place, based something like that. So it's just a structured, graphically structured knowledge. So there are 2 node types. There are entity types and value types. So entity types are like Mona Lisa, Da Vinci are entity types. Value types are person. So like Da Vinci is a person. Paris is a place. So like there are 2 types of nodes, and the edges are directed and multi-type now. So edges are directed. For example, Da Vinci painted Mona Lisa, but Mona Lisa did not paint Da Vinci. So it's a unidirectional relationship, and there are a lot of types. So like painted by, located in, is a, likes, friend of, born in, something like that. So there are a lot of edge types, and this is something called structured knowledge is. Usually when we say structured knowledge in NLP, we usually refer to either graphs or tables. So tables being like database tables. And this also is a popular topic these days. Like people try to do like knowledge grounded reasoning or common knowledge ground reasoning. Like when you do question answering, like squad data set, some questions are unanswerable unless you have access to common knowledge. So like there's common sense QA now. So it's question that requires some level of common sense. So common sense is given to you as a graphical structure, as a graph. So you need to refer to the graph and also the reference text to answer the question. So that's called common sense knowledge. Common sense question answering, common sense QA. All right, yeah, this was a overall view of, we still have 2 more actually. So generally speaking, everything is a graph. So even like sequences are special case of graph, like A after B, B after C, C after, like words, like he is a bad student or whatever. Like this, like a text is a special case of graph, or specifically it's a directed chain. there's direction here. It's directed edges, and it forms a chain. So sequences are a special case of graphs. Images are a special case of graph as well. So this would be a undirected grid. So it's a if you have 4x4, like resolution 4x4 image, then it's a 4x4 grid. So everything like it's so each pixel or each node has 4 neighbors. Like this one has 1, 2, 3, 4 neighbors. So all pixels or all nodes have 4 labels, and it forms a grid. So it's also a special case of graph. So everything, like, you can treat anything like a graph. So graph itself is a very general concept. Like anything you could see could be a graph if there is structure. If there is a certain structure and it consists of nodes and edges, then it's a graph basically. All right, so yeah, so that was the overview of the graph data, what graphs are. And any questions so far? 당연하죠. 3D 그래드도 가능합니다. 이런 식으로 이렇게 3D로 그래드를. Yeah, 3D grids are also a thing. So people, yeah. So, and then you have like a, if you're doing 3D convolution, then you have a. Let me draw it with another color. If you're doing 3D convolution, then what you're doing is basically you have like 1, 2, 3, a filter that is also a grid, and then you're moving this filter around like this way or this way, basically. Anyway, yeah, good question. All right, if there are no more questions, we'll move on. It could also become like 4D grids, although we can't draw it, but theoretically, you know, in a 4-dimensional space, there could be 4D grids. 레이블링 되어 있는 데이터들이 많이 있나요? 사실 그 캠펍인가? 펍캠인가? 잘 기억이 안 나요. 캠펍 또는 펍캠이라는 데이터베이스가 있는데, 거기 가보시면 이제 그 케미컬 컴파운드들 수십만 개 또 수백만 개가 있고, 걔네들의 그 화학적 특성들이 다 그 기재가 되어 있어요. 얘 녹는 점, 끓는 점, 뭐 무게, 그다음에 뭐 그런 것들 있잖아요. 뭐 무슨 물리량이나 화학적 특성들이 적혀져 있는 그 데이터베이스가 있거든요. 그걸로 이제 뭐 셀프 슈퍼바이즈 러닝을 한다던가 뭐 그런 식으로 할 수 있겠죠. 네. All right, moving on. So I was just talking about a potential database for chemistry, chemical compounds with a lot of information per compound, like the melting point, or like or boiling point, or the weight, something like that. All right, let's move on to graph convolutions, which is the core material of today. So what we want to do is trying to come up with a graph representation. So like so far, everything in deep learning, everything was just representation learning. So the goal is, how can we represent graphs? So images can be represented by convolutes, for example. Like images are represented by convolutes. So if you have a 128 by 128 RGB image, you put it through Resident, and then you get a final 2048 dimensional feature vector. After you do global average pulling, then you get 2048 dimensional feature vector. So that's your graph representation. And text can be represented by either RNN or BERT, for example. If you have a 28 token text, like, I don't know, some text basically, and then you put it through RNN or BERT, then you have essentially 20 contextualized embeddings. So one contextualized embedding per input token. Or you could have you could take the last token of the last hidden layer of RNN and treat that as a text representation, the entire representation of the entire 20 tokens, or you could do a like attention on top of RNN to get the final text representation. In case of BERT, you can use CLS embedding to represent the entire text, for example. So that's how you do with images and text. So in case of graphs, what kind of representation do you want? For example, first of all, what kind of representation do you need or is required out of graphs? So graphs are basically it's a data set consisting of V number of nodes and E number of edges. So what you want is probably representation of nodes first. So you want to get the node representation. Like if you have a social network, then you want to get the representation of each person. If you have a chemical compound, then you want to get the representation of each node. I mean, each atom or something like that. And possibly you might want to get an embedding of the edges as well, which is not super common, but sometimes like there could be a task where it requires you to learn the edge embeddings. And also I forgot, actually, you might want to also have V embeddings and also embed the graph itself, the G embedding, the embedding of the graph, the entire graph, like CLS embedding here. CLS embedding represents the entire text. Same manner, some embedding, some G embedding represents entire graph. So for example, like if you want to do a graph level prediction, like the melting point of some chemical compound, or toxicity level of some chemical compound, or the compatibility or effectiveness of COVID-19 drug, something like that, then that's a graph level embedding. I mean, that requires graph level embedding. But if you want to do like link prediction, like given two random nodes, if the two nodes should be connected or not, so that's link prediction, then it requires node embeddings. So there are two levels of embeddings. So it's individual node embeddings and the entire graph embeddings, based on what kind of task you're facing. All right, so why can't we use combinates? So okay, there's a question. Nodes of the graph don't have to be the same data, right? Like images can be connected to some textual content. Yeah, exactly. Nodes of it could be a heterogeneous multimodal graph. The members of the graph doesn't have to be the same data type. It could be anything. Like electronic health records are great examples of heterogeneous multimodal graphs. Like it's connected to images, text, continuous floating point values, integer values, whatever. So yeah, again, so why can't we use convness on graphs? So that's because convolution filters, the filters or the kernels of convnets assume same number of neighbors all the time. So like here, as I said, if you're facing some grid type data, then you're assuming that each node or each feature or each pixel has 4 neighbors all the time. 4 neighbors, like here, 4 neighbors here, again, 4 neighbors here. So that's how you can slide your kernel or filter across the space, like horizontally and vertically, and that's how you represent your image. But general graphs don't assume such thing. So it doesn't assume that there will be always the same number of nodes all the time. Like here, this has three neighbors, 1, 2, 3, but this one has only 1 neighbor. So you never know that how many neighbors a node will face. So you can't use convolutional neural networks or conv-filters. But what you can do is you can take the core principle of confident filters. So what confident filter does is basically it's aggregating features from the local neighbors. That's the essence of confident filters. So it's just local information that really matters in images and also in graphs, actually, because as I said, images are graphs, actually. So what we did in images is we had like a 3 by 3 filter, like three 3x3 filter, and we slide it across the surface, across the image. And what we did in each time step is multiplying this by this, this by this, this by this, this here, like multiplying each pixel to the corresponding weight and then summing them up. So it's a weight summing operation per time step. And the weight sum was applied only locally to the neighbors of this particular target. So that was graph convolution. That was image convolution or convoluted filters. So we can take that core principle, which is to aggregate features from the local neighbors and then apply it to graphs. And that's it. So the core principle of graph convolution is relatively simple, actually. So if you're given a graph, a G, which consists of V nodes and edges, at each time step, what you do in graph convolution is super simple. At each node Vi, so at some ith node, you want to aggregate all neighbors' features. So all neighbors, meaning all connected nodes. So mathematically, you could write it like this. So here the AI is set of nodes connected to the ith nodes. So if there's like something like this, like let's say that this is I, and this is like I is not a good thing. Let's say this is, so this is 1 2 3 4 5 6 7 8, and so the A5 would be what? It would be 3 4 6, right? 3 4 6. So that is the AI or A5 in this case. So set of nodes connected to ith node. And what you want to do is you want to sum the features of those neighboring nodes or connected nodes. So you take some function that extracts the features or represents, maybe embeds, basically. So you want to take the embedding of 3, so some embedding of 3 plus some embedding of 4 plus some embedding of 6. So you want to sum them up, and that's how you aggregate all neighbor features of the node number 5. So that becomes A5. So A5 here. So that's the aggregation part. So aggregating your neighbor's feature is the aggregation part. And then once you've done that, you want to move on to the combination part. So combine VI's feature, the target, the center node's feature with neighbor's feature. So you've aggregated neighbor features, and now you want to combine it with the features of the center, so the target node itself. So FV and AI, and you want to combine it with some other function, G function. It could be a sum function. It could be a max pull function. It could be mean pull, average pulling function, whatever. Some combination features, basically. And that's how you get HI, which is the node representation of the ith node. So ith node feature is HI. So a representation of node VI. And that's it. That's the essence of graph convolution. Aggregate and then combine. So let's take a look at it in a more linear algebra flavor. So how you want to do it in a like a matrix style, like linear algebra style, is, first of all, in order to aggregate your neighbor features, you need to know which one's connected to which, like how the connection information, and connection information, or the structure, graphical structure information, is usually represented as adjacency matrix. So given a graph like this, so it's a rather hierarchical looking graph, or not a tree. It's not a tree because this guy has 2 parents, so it's not a tree, but it's a hierarchical graph, and it doesn't have any node specific features. It's just nodes are nodes, and also it's not, there are no directions, so it's undirected graphs. So it's undirected graph, and the adjacency matrix of this graph looks like this. So I forgot to write down like the node numbers, like node number 1 2 3 4 5 6, and 1 2 3 4 5 6. And as you can see, node number 1 is connected to 2 and 3. So node number 1 is connected to 2 and 3. Node number 2 is connected to 1 4, 5, 1, 1. So this guy's connected to 1, 4, 5. And same manner, like 3 is connected to 1, 4, 1, 4, 6, 1, 4, 6. 4 is connected to 2 and 3. 5 is connected to only 1, which is 2. 6 is connected to only 1 node, which is 3. So that's how you represent a graph in an adjacency matrix. And if this was directed, then this will no longer be a symmetric matrix. For example, for now, it's undirected graph. So it's a symmetric matrix. Like the upper triangular and the lower triangular have the same contents, have the same values. But if this were a directed graph, then there's no guarantee that this would be a symmetric graph. I mean, symmetric matrix. For example, like if this was a directed graph and like 2 had outgoing edge to 1, then this would survive, but this would not, because 1 is no longer connected to 2. Only 2 is connected to 1. But we're dealing with only undirected graph here. Right, moving on. So this is adjacency matrix, and now you need something called node index and node embedding vector. So node index is like, this is node number 1, this is node number 2, 3, 4, 5, 6. So that is node index. And when you have node index and you multiply it with some embedding vector, basically an embedding matrix, then you can have these node embeddings or node features like this, like XW. So W being some matrix, and what you need is just 6 rows here for now. One more row now. So the first row would be the embedding for the first node number 1. So this is embedding. This is embedding of node number 1. This is embedding of node number 2. This is embedding of node number 3, all the way to embedding of node number 6. So this would be your W, and it would be a trainable matrix. It's a learnable parameter. Just like word embedding, there's just node embeddings now. And given node number 2, then you can retrieve this one. If you're given node 6, then you can retrieve this one. So basically, if you multiply your node index X with your node embedding vector or node embedding matrices, this could be a matrix actually. This is a matrix. Node embedding matrix, then you can get this one, this node embeddings, and now you have a adjacency matrix and node embeddings. Now if you multiply them, if you multiply the two, so AXW, A times XW, then what you get is this basically. So you multiply this, you do an inner product with this row and this column, or actually this is a matrix too, but we'll forget about the column values here. So take this one and multiply that, do an inner product with this, and then you get FV2 plus FV3, because only this will survive. So this plus this becomes this. And if you do inner product with this row and this matrix, then what you get is this, because only first and fourth and fifth node embeddings will survive. So you do this with this row, this row, this row, this row, and that's how you get 6 rows here. 6 rows. Or basically 6 rows. Matrix with 6 rows. And each row is a certain summation of the connected components. So I hope this is pretty clear to everybody. And moving on to the next one. So is AXW, is this a node representation H? Like, is this itself? Is this the node representation of node number 1? Is this H1? Or is this H2? And can this be H6? Like, are they enough? And the answer is, anybody care to answer? Can they be a good representation of each node? No. Why is it a no then? Exactly, yes. We need to combine. Very good. We need to combine. So this so far was just neighbor aggregation. Exactly. This was just neighbor aggregation. So we're looking at node number 1, but the contents of node H1 or potential H1 is just FV2 plus FV3, which are the neighbors of the node number 1. So what we did with AXW is just neighbor aggregation, and we need to still somehow combine FV1 with these somehow, at least sum them up, or do max pooling or mean pooling or something. So this is not over. We need the combination step. So how we can achieve that is we can have a another modified matrix, A prime, which is just a sum of adjacency and the identity matrix. So now you can take a look at 1, 1, 1, 1, 1, 1 here. So the before it was, these were all zeros, but now the diagonal elements are all ones. And if this effect of having this diagonal elements all one is A prime XW is now contains FV1, because now if you take a look at like this row, do an inner product with this, then it's sum of this guy. In the same manner, if you take a look at this row and this inner product, then now it's sum of this guy, this guy, this guy, this guy. So now, if you take a look at each row, then the target nodes feature also survives. So basically, it's just, I mean, it's not a fancy combination. It's just a sum. So because you're summing the target with this neighbor, target with this with this neighbor, target with this neighbor. So it's just a simple sum. But still, we are combining its original, the target node's feature with its neighbors. So as far as we're doing that, it's fine. So A prime XW can be a node representation now. So this can be a good H1. So this much now we understand, right? Having a modified adjacency matrix and multiplying that with node embeddings leads to at least we fulfill the necessary condition, basically. But moving on. But there is still another problem, which is the scale of node features. Scale of node features differ by the number of neighbors. So if we were to treat this as a node representation matrix H, then potentially, for example, H2 could be twice as large as F5, because H2 is the sum of 4 node features, but H5 is sum of 2 node features. So depending on how many nodes you're connected to, your representation could be larger or smaller than some other node representations. And we don't want that. We want to have, like, normalization is really important, as we've seen it so many times so far, like with batch norm or layer norm, like those kind of stuff. Normalization is a very important issue, and we don't want to have unnormalized node representations most of the time. There are some very specific cases where we must not do normalization, like having differently scaled node representation may be important in some tasks, but in most cases, we want to obtain a normalized node representation. So simply what we can do is we can introduce something called degree matrix. So degree matrix is a diagonal matrix where the diagonal elements are number of edges. So for example, here, I forgot to draw the degree matrix here, but for this particular guy, a degree matrix would be 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the first guy is connected to what? Is connected to 2 nodes. And the second guy is connected to 3 nodes. Third guy is also connected to 3 nodes. Fourth guy is connected to 2 nodes, and 1 and 1. So that's it. But so that is your degree matrix. But here we are using a modified adjacency matrix. So actually, the effect of having a modified adjacency matrix is you're adding self loops here, like this. You're adding self loops. Actually, self loops are. There shouldn't be a direction here, right? So it's just undirected self loop. Like there shouldn't be an arrow. It's just undirected loop. So adding the diagonal elements is the same as adding a self loop. And since there are self loops now, like here, the degree matrix should be each element of the degree matrix should be added the value 1. So it should be 3, 4, 4, 3, 2, 2. So it's actually D prime, D prime. And inverse of the inverse of the degree matrix, D inverse D to the -1, So it's simply just it's just a reciprocal. So it'll be the inverse would be like 1/3, 1/4, 1/4, something like that, basically. So yeah, I won't draw it, basically. So D inverse is like this reciprocal of this guy. And if you multiply D inverse with A prime, then what you get is, before it was 1 1 1, it was 1 1 1 1 1 1 1 1 1 1 1 1 1, like that, like 1 1. Now if you multiply A prime with D inverse 1, then you're multiplying, basically you're multiplying 1/3, 1/3, 1/3, and that's how you get 0.33s. And now you're multiplying 1/4 to all the row values here, 1/4 all the values here, 1/3 all the values here, 1/2, 1/2. And that's how you normalize your adjacency matrix. So this is actually a normalized adjacency matrix. And now you multiply the inverse A prime, the normalized adjacency matrix, with node embeddings, then now you get this one, which is now a normalized node representation vectors. You multiply 0.33 to all the values here. You multiply 0.25 to all the values here. Like basically you're obtaining, or you're calculating the normalized node representation for each node 1, 2, 3, 4, 5, 6. So let me erase this guy. So now this one is a normalized node representation vectors. But this is still not enough, because all the operations so far was all linear operations. D inverse A prime X W, these are all just matrices. And what we did so far was just bunch of matrix multiplications. So we simply need a nonlinearity, and how we do it is we encapsulate the entire thing with some nonlinear functions. Could be ReLU, could be sigmoid, could be whatever, could be anything, could be tan H, up to you. So this is the same thing, like D inverse A prime X W, and then encapsulate that with a nonlinear activation function. So this is your graph convolution, and that's it. So this is your graph convolution. Nonlinear, like D A prime, the modified adjacency matrix, degree matrix, nonlinear activation, and W. So all you need is this. And the only learnable parameters are this one, W. So X is the node index. It's like which nodes are there in your graphs. And A is also determined by the graphical structure, because you know the graph structure of the graph. D is also determined by the graphical structure. So the only thing that is learnable is W here. Question. 다이아고널 타임만 있으면 셀프 노드가 몇 개인지 구분할 수가 없게 되는 건가요? 셀프 노드가 뭔가요? 다이아고널 타임만 있으면은, 기본적으로 모든 노드들은 스스로를 셀프 룹이라고 제가 표현을 했는데, 그러니까 모든 노드들은, 그러니까 그래프 컨볼루션 할 때는 모든 노드들이 다 자기 스스로를 참조한다고 일부러 강제를 합니다. 여기 보시면 여기 다 1을 더해줬듯이, 그냥 그래프 컨볼루션 할 때는 기본적으로 자기 참조를 하게 시켜요. 그러니까 이게 이렇게 여러 개가 있다는 게 그거 의미하시는 건가? 잘 모르겠네. 셀프 룹은 하나밖에 없습니다. 1이 자기 스스로 참조한 거는, 자기 스스로 여러 번 참조하는 게 무슨 의미인지 모르겠는데, 네. 이해하신 것 같네요. 네. Alright. Alright, yeah, okay. So this equation is the essence of graph convolution. And the problem, I mean, not the problem. I mean, what we did so far is just taking a look at a single graph convolution, which means that this is an aggregation of neighbors just one hop away. So given this graph, and we do a sigmoid, not sigmoid, some nonlinear D inverse A prime XW. If you do this, then what you're doing is, for example, in perspective of node number 5, what it has is it aggregated, it took the node feature of 2 and then combined it with itself, so it's 5 plus 2, basically. In 2's example, in 2's perspective, what it did is it aggregated this guy, this guy, this guy, 145's features, and combined it with itself. So 2 plus 145. So that is simply what we did in the graph convolution. And basically, as I said, this is just aggregating neighbors just 1 hop away. And if we want, how do we aggregate neighbors of 2 hops away then? Like, what if we want to go more than that? What if we want to aggregate further features that are further away, that are farther away from yourself? Like maybe node number 2 wants to aggregate feature from node number 3, which is 2 hops away. Then how would we do that? It's simply how we, yeah, I'll just reveal the answer. So how we would do it is we simply just do it one more time. So if we call this H1, then you can do another graph convolution, H1, plug H1 here instead of X. So it used to be X here. And we simply plug H1, which is the former, which was the graph or node representation vectors from the former graph convolution, and then do the whole thing again with another learnable parameter. This is not the same as W from the previous. Not the same thing. So W2 is another learnable parameter, and you plugged in H1 instead of X, and then that's how you get H2. And what the effect of this is simply, for example, this was your H1. So 5 is already 5 plus 2, 2 is already 2 plus 1 plus 4 plus 5. And if you do one more graph convolution, one more GC, then in 5's perspective, what you do is you are again aggregating in 5's perspective. Now you need to aggregate those features of 2, which is essentially 2 plus 1 plus 4 plus 5 now. And you want to combine it with yourself, which is 5 plus 2 now. So it's now 5 plus 2, which was your previous self, 5 plus 2, plus 2 plus 1 plus 4 plus 5 here. And now that's how you essentially get node information from 2 hops away, because 4 is 2 hops away from 5. So 1, 2. And 1 is also 2 hops away from 5. 1, 2. So by repeating graph convolution 2 times, you've essentially gathered information from nodes that are 2 hops away. So if you do it 3 times, then it's aggregating from 3 hops away. If you do it 4 times, then you're aggregating information from 4 hops away. So basically, that's how you repeat your graph convolution and aggregate node features from distant neighbors, basically. So you can generalize it to HK. So if the kth round or kth time step feature of node representation is basically based on previous node features multiplied by this new learnable parameter, and the same deal here and the same deal here. Question: do we need directed graphs by simply changing? Do we model directed graphs by simply changing it? Yes, exactly. If you just need to change the adjacency matrix, and that's how you obtain directed graphs. And if you have multi-type edges, for example, yeah, let me just erase all this. Actually, no, let me erase this. So if you have multi-type edges, like the edge type here and edge type here are different, then you probably need let me see. XW, you need nodes. Yeah, you probably need another matrix here. Because the first matrix will represent a certain edge type. And for example, if this edge type was like friends, and this edge type was family, and your first matrix could be friends matrix, and your second matrix would be family matrix, then no longer 1 and 2, no longer 1 and 3, the relationship between 1 and 3 should be here, because this is friends matrix, and 1 and 3 are not friends, they're families. So this should be 0 here, and actually there should be 1 here, like 1, 2, 3, 4, 5, yeah, 1, 2, 3, 4, 5, yeah. So like 1, 0, 1, basically like this. So And you might want to have like another set of node embeddings as well. 네, 제가. All right. Yeah, I accidentally answered question from Yonghee. All right. Okay. So far we've derived this guy, and there are a lot of graph convolution variations. So this is the essence of graph convolution. This, like, repeating this process is graph convolution, and there are a lot of different varieties. So different normalization. So instead of D inverse A prime, Maxwelling and I forgot Kipf. So Kipf and Welling are the guys who actually came up with this graph convolutional neural network concept, with like this concept for the first time, which is called semi-supervised classification with graph convolutional neural networks, which was presented in iClear maybe, or NeurIPS, I forgot. Anyway, it was a very famous paper. This actually like sparked the interest of graph convolutional neural networks. And in that paper, they actually came up with this normalization rather than this normalization. And the reason is because this is no longer, like, this is more interesting. This is no longer like symmetric. If you think about it, like, this will give you basically a very simple looking matrix like this. But if you do a D half inverse A prime D half inverse, then the values here wouldn't be the same anymore. Like D inverse A prime, the values here are all the same, but like if you do this, the values here wouldn't be like 1 over 3, 1 over 3, 1 over 3. It'll be something different. So that actually, like, they say that actually produces more interesting dynamics. And the whole thing, I mean, the graph convolution, the whole concept of graph convolution is motivated by spectral graph convolution theory. So which is like a whole theory behind like graph Laplacian and graph Fourier transform and those kind of stuff. So like you can have, based on the adjacency matrix, you can derive graph Laplacian, and then you can actually derive the eigenvectors and eigenvalues of that graph Laplacian, and then you use that eigenvectors to transform the node embeddings into some other like spectral domain representations, and then you can do a lot of interesting stuff, and like, you know, graph cut problems or graph clustering problems, something like that. But we won't go into detail. It's like very complicated stuff that I kind of don't really know the details of. Anyway, yeah, just suffice to say that graph convolution is like, it has a lot of theory behind it. And actually, this guy is it's like a rank, like crude approximation, like some numerical, some approximation of this spectral graph convolution, basically. And it actually works pretty well in practice because it's neural networks. Different combination steps could also exist. So instead of summation, instead of summing up, you can actually use another linear layer, like this G here. When I was combining the target nodes feature with neighbor features, I simply sum them up. But you can actually do like you can concatenate them and then do a simple linear multiple linear. You can add a linear layer to combine them. So, and also another variation is actually using RNNs per each node. So here, if you did like H1 to H2 to H3, you were actually, what you did is you were actually just still keep adding and adding and adding. So here, you were adding here, and then you were adding here. So that's kind of like RNN. Like in this guy's perspective, this guy's representation is keep being added and added and added the features from farther away neighbors. So that is kind of like RNN. And some people actually made them a full RNN with GRE or LSTM. So actually, they use LSTM to represent the node representation. So more sophisticated way to accumulate n-hop information. And there are a lot of, there are a whole lot more variations, and they are all called, the whole family is called graph neural networks these days. So yeah, this is the essence of graph convolution. All right, moving on to the final chapter, GNN and Transformer. There's a question. W embedding matrix transform solution. W는 어떤 의미가 있는 건가요? HK-1만 있으면 되는 거 아닌가요? 아, 그런데요. 네, 예, 맞습니다. 네, 근데 이것만 있으면은 결국 스스로 섞는 것밖에 안 되고 한 번 더 또다시 representation 파워를 올려주기 위해서 WK를 계속 넣어주는 거예요. 이제 계속 한 번씩 리니어 트랜스폼 해주고 네이버 섞어주고 넌 리니어로 끝내주고 다음번에 다시 또 리니어 트랜스포메이션 해주고 섞어주고 넌 리니어 해주고 그 다음번에 또 다시 리니어 트랜스폼 해주고 섞어주고 넌 리니어 해주고 그걸 계속 반복하는 겁니다. 기본적으로. 안 그럼 네 그래야 그러니까 이 딥러닝의 뉴럴 네트워크 레이어에서 매 레이어마다 매트릭스가 계속 있잖아요. 이 리니어 뭐지 웨이트 매트릭스 그러니까 모든 레이어가 WX 플러스 B 시그마 다시 W 플러스 B 시그마 다시 W 플러스 B 시그마 이런 식으로 되잖아요. 그러니까 그거랑 똑같은 거예요. 그거랑 똑같은데 이거는 fully connected일 때고 요거는 이제 그래프일 때고 그 차이입니다. 그러니까 웨이트 매트릭스는 매 레이어마다 필요합니다. All right, so we only have 8 minutes, so let's kind of speed it up. So I hope that self-attention is really now like everybody completely knows self-attention, hopefully. So just a simple recap, like if there's a sentence, I like going to movies, then self-attention is like I attending to everything else and like attending to everything else. And of course, it is attending to itself too. It is attending to itself too. So that is self-attention. And if you remember the QKV operations, these scale dot product operation of self-attention, then this part was softmax of the QK transpose divided by square root of D. This guy produced a attention map, which is a normalized probability matrix basically, and V was the text token embeddings or word embeddings, and multiplying them gave you this weight sum of the word tokens. And now you can clearly see the similarity between self-attention and graph convolution, because this guy is also normalized. So sum over this guy is 1. Sum over this guy, this axis is 1. Same here. Sum over this row is 1. Sum over this row is of course 1 because we normalized it. And there's a node embedding here, and there's word embedding here, token embedding here, and you just weight sum them, and you get this guy. Weight sum them, and you get this guy. So those two are essentially doing the same operation, QKV operation and graph convolution. And the only difference is in graph convolution, these values are fixed. Like when you so in self-attention, in transformer, you repeat self-attention multiple times by stacking like 6 blocks, 12 blocks, 24 blocks. Like you're repeating self-attention multiple times, and at each repetition, this guy changes. Like the contents of this guy, the value of this guy changes per block because you're using different WK, different WV, different WQ in each block, basically, each block. So I'm just gonna say teeth block. But in graph convolution, when you repeat graph convolution multiple times, you're using the same normalized adjacency matrix over and over again. So that is the only difference. So self-attention, it doesn't know the graph structure. So it implicitly assumes everything is fully connected. So everything is fully connected in self-attention, and you're learning the edge weights during training. So the edge weights being the attention score is learned during training. They're obtained on the fly. So and in self-attention, node embeddings or token embeddings are learned in a data-driven fashion, purely data-driven fashion, because you don't know the structure of graphs. In graph convolution, you do know the graph structure. So there's prior knowledge on the graph structure. So the graph structures are fixed in repetition of graph convolution. So learn node embeddings based on the fixed adjacency matrix. So that's the only difference between self-attention and graph convolution. So mathematically, graph convolution, so I'm using MLP instead of sigma now. So MLP. So D inverse A prime, C being the node index or the previous node representation. So this could be H, but I just wrote it as C this time. So The new node representation is just NLP of D inverse A C W, and transformer, the QKV operation is a transformer, or actually the transformer encoder block itself. Encoder block itself could be simplified in this format, because if you remember, in encoder there's self-attention, then there's layer norm, there's layer norm, then there's feed forward, then there's layer norm, and then there's like a residual connections like this, and that was your encoder. But if you forget about this guy and the residual connection, if you forget about this, then all you're left with is self-attention and feed forward, which is basically multi-layer perceptron. So here, multi-layer perceptron with QKV operation, which is the self-attention. So that is the simplified form of transformer encoder. And as I said, this guy is the QKV, this guy and this guy. So this guy's a node, this guy's a word embedding, this guy is the self-attention map. So there's one-to-one correspondence between graph convolution and transformer. So this guy here and this guy here, the normalized adjacency matrix and self-attention are compatible basically. And this guy, the node embeddings, and this guy, the word embeddings here, which is here, word embeddings here. It has the same equation. C time the node embeddings from the previous time step plus the embedding matrix, word embeddings from the previous time step and previous block, and the word embedding matrix. That's it. So those two are like interchangeable. So there are some people actually have focused on this relationship between self-attention and graph convolution. So there came there's a work called graph attention network, which is a lot of people use these days. So it's basically learning the edge weights with attention. So what they do is they zero out the probability of non-connected edges. So you already know the adjacency matrix. So for example, in let's go back to the previous case here. 1, 2, 3, 4, right? And previously it was 1, 1, 1, 1, 1, 1, 1. 1, 1, 1, 1, 1, basically something like this. So instead of using a normalized adjacency matrix in graph attention networks, they try to learn the edge weights of like the attention, learn the attention on the connected component, on the connected edges. So they actually have they use a negative infinity matrix basically to mask on top of the QK transpose divided by square root of D. So basically here. So if you multiply a negative infinity matrix here and then do softmax, then basically you're zeroing out the probability of non-connected edges, and that's it. So that was simply changing the adjacency matrix to a attention. Actually it was a very like a simple idea, but very like robust approach. It works pretty like graph attention network works really well on a lot of tasks actually. So a lot of people use this as a backbone network when they have graph to handle. So graph attention networks, and this learning this, you can actually learn the structure of graph with attention. So this is my paper from when I was before I left Google. So this is also based on the fact that the graph attention, self-attention, and graph convolution have a very tight connection. So you can actually use self-attention to learn the underlying graph structure. So for example, if you are given a data set which you know is a graph, but you don't know, or you only partially know some which are connected to each other. Like if you only know the if you have partial information on the graphical structure, then you can use self-attention to fill the remaining information, like which is connected to which. So you can start with a prior knowledge driven adjacency matrix. So you can have an adjacency matrix with constructed from prior knowledge, then gradually evolve with self-attention. So you have like a lot of graph convolution blocks, like block 1, this is block 1, block 2, block 3, like repeating the graph convolution. You start with a fixed adjacency matrix that is derived from some domain knowledge. For example, domain knowledge being conditional probability between pairs of nodes. Like there are, like you can go through the training example and see which pairs of nodes are co-occur more often than others. So basically, basically calculating the conditional probability between pairs of nodes, and then inject that information into the adjacency matrix. Then you start from that. So this is adjacency matrix. But from block two, you do self-attention now. Self-attention. So you gradually evolve from adjacency matrix and then do self-attention again and again and again. And you try to make this self-attention map as close as this guy as possible. So you use some regularization scheme. So that's how you learn the graphical structure of a data set that you don't know the complete structure of. So that's called graph convolutional transformer. And there are probably a lot more variations on this. Like this concept is pretty interesting, like self-attention and graph convolution. So this concept is pretty interesting. So there are a lot more works, not a lot, but I'm pretty sure there are more works trying to exploit this relationship between the two when handling either text or handling graphs, basically. All right, it's 12:03 now. Okay, so we made it in time this time. So this is the end of the class. Any questions so far? I hope this is super simple. I mean, if you were asked to implement graph convolution graph neural networks on PyTorch, all you need to do is basically, all you need to do is just implement this and then repeat this multiple times. It's simpler than transformer, basically. It's simpler than transformer. So I hope this has been a very easy class for you guys. And if you want to be fancy, you can use graph attention networks too. But in the practice session on Thursday, basically we'll just implement this, or even just simple nonlinear activation instead of MLP. All right. Any questions so far before I end the class? Nope. Okay. All right. Thanks. Thank you, everybody. Then no more questions. I'll see you guys on Thursday. Bye-bye. 마지막 질문 있으시네요. 네, normalize는 보통 합니다. 네. 그리고 헬스케어 데이터에서는 이제 뭐 continuous value, floating point value도 있기 때문에 그거를 애초에 그것부터 normalize를 0, 1 또는 마이너스 1, 1 사이로 이제 해버리고 그 다음에 그거를 적절하게 그 discrete feature들이랑 섞어줘야 되거든요. 그 부분부터가 이제 일반적인 그래프 뉴럴 네트워크 그래프 데이터랑은 좀 달라가지고 이제 헬스케어 데이터는 조금 처리를 조심스럽게 해줘야 돼요. 근데 어쨌든 노멀라이제이션은 항상 들어갑니다. 턴 프로젝트는 이번 주말에는 나올 거예요. 턴 프로젝트는 적어도 다음 주 월요일까지 나올 겁니다. 디스크리트와 컨티뉴어스를 섞는 거는 글쎄요, 그거는 뭐라고 찾는지 모르겠는데 보통 섞는 방법은 두 개 있습니다. 그냥 디스크리트 데이터랑 컨티뉴어스 피처를 컨캣하는 방법이 있고, 그게 아니면은 이 디스크리트 피처마다 가질 수 있는 그 컨티뉴어스 피처가 있는데 뭐 혈압이 얼마라든가 그런 걸 아예 버켓타이즈를 해가지고 예를 들어서 뭐 혈압이 이제 160부터 80까지 그 사이에 레인지가 있으면은 그거 이제 그 구간을 5구간을 나눠요. 이제 퍼센타일을 100에서 80%, 80에서 60% 이런 식으로 퍼센타일로 나눠가지고 뭐 5버켓 또는 10버켓을 나눠서 그거를 또 다시 디스크리트 피처로 취급해버리는 수가 있거든요. 그러니까 이제 혈압이란 피처를 혈압 플러스 컨티뉴어스가 아니라 혈압 자체를 혈압 고구간, 혈압 저구간, 혈압 중간 구간 이런 식으로 이제 여러 개의 디스크리트 피처로 나눠버리는 방법도 있습니다. 보통 그 두 개의 방법을 사용을 해요. 아니면 뭐 포지션 인베딩처럼 컨티뉴어스 피처를 이제 벡터로 만든다면 그걸 더해버릴 수도 있고 디스크리트 피처랑 방법이 하나는 아닙니다. 그래프 컨볼루션 베리에이션 다른 노멀라이제이션 방법, 요 방법이 그러니까 그러니까 우리가 아까 제가 설명드린 노멀라이제이션 방법은 D 인버스 A 프라임이었는데 그게 아니라 이제 이거를 2분의 1, 2분의 1 인버스식을 한다는 거예요. 그러니까 이제 D가 아까 뭐 3분의 1, 4분의 1, 4분의 1, 뭐 3분의 1, 2분의 1, 2분의 1 뭐 이랬는데 그게 아니라 이거를 이제 루트 3분의 1, 루트 4분의 1, 루트 3분의 1, 루트 2분의 1 뭐 이런 식으로 한다는 겁니다. 이런 식으로. 이걸 해가지고 이거를 양쪽에서 곱해주면은 이거 대신에 이렇게 곱해주면은 이렇게 해주면은 그러면 더 이상 이렇게 normalize adjacency matrix 한 로우에 밸류들이 다 똑같이 33, 33, 33, 25, 25, 25 이렇게 안 나와요, 더 이상. 그러니까 이거는 D 인버스 A를 했을 때 이제 이렇게 나오고 만약에 D 2분의 1 A 프라임 D 2분의 1을 했으면은 얘랑 얘 밸류가 다 다르게 나오거든요. 이렇게 똑같이 똑같은 밸류가 나오지 않아요. 그래서 그렇기 때문에 요 그래프 컨볼루션 하면은 더 재미있는 더 뭔가 흥미로운 다이내믹스가 발생을 한다라는 게 이제 요거의 어떤 모티베이션, 요 노멀리티의 모티베이션입니다. 그리고 이제 이렇게 하는 게 사실 그래프 라플라시안이라는 게 있는데 그래프 라플라시안이라는 게 디그리 매트릭스에서 이제 어제이선스를 뺀 게 이제 그래프 라플라시안인데 제가 헷갈리는데 맞을 거예요. 아마 디그리 매트릭스에서 이제 어제이선스를 뺀 게 그래프 라플라시안인데 그래프 라플라시안에서 양면에다 D 인버스 이렇게 곱해준 다음에 이렇게 뭘 하면은 그렇게 한 다음 또 이제 뭐 이렇게 아이겐 이렇게 스펙트럴 티어리를 스펙트럴 디컴포지션 하고 이러면 그래프의 특성을 잘 반영하는 노드 피처들이 나오는데 그런 데서 이제 영감을 받아가지고 이렇게 요걸 여기다 갖다 쓰는 거였을 거예요 아마 제가 기억하기로. 성능적으로 유의미하냐고 성능적으로 이렇게 쓰는 사람들 제 느낌상 제가 그래프의 전문가는 아니지만 느낌상 큰 차이는 없습니다. 이렇게 하든 큰 차이는 없어요. 둘 다 해봐도 되겠죠. 사실상. 네. 네, 어차피 그래프 어텐션 네트워크를 쓰게 되면은 이게 더 이상 무의미해져요. 그러니까 그래프 어텐션 네트워크를 쓰면은 여기 요 D 인버스 A 대신에 소프트맥스 오퍼레이션이 들어가가지고 노멀라이제이션을 해주기 때문에 더 이상 D로 강제적으로 노멀라이즈 하는 게 의미가 없어지거든요. 그렇기 때문에 이제 그리고 그래프 어텐션 네트워크가 워낙 로버스트하고 여기저기서 다 잘 돼가지고 네, 이런 거에 이제 이렇게 그다지 막 신경을 쓰는 사용자들이나 연구자들이 있는지 잘 모르겠어요. 알겠습니다. 감사합니다. 그럼 네, 여기서 마치도록 하겠습니다. Alright, thank you everybody. Bye bye.